Okay, in 2.1 and 2.2, we are introducing ourselves to derivatives as well as exploring some basic differentiation rules. And so with this first kind of page and a half, we are delving into that introduction side of the notes. What is a derivative? So, like, what is the purpose of a derivative? How do we notate a derivative? What's the difference between continuity and differentiability? After we take a little bit of time discussing these things, then we'll jump to our derivative rules. Okay, so what is the purpose of a derivative? Well, derivatives actually have a variety of uses. You see some of them notated underneath derivative uses here, but in our class, we are, for the most part, going to use derivative to find the slope of a tangent line. And this actually is important to recognize because within the directions of your problems, they will sometimes tell you find the derivative of, and other times they will say find the slope of the tangent line of. And those are the same directions for all intents and purposes, right? The slope of the tangent line is a purpose for a derivative. And so when you read something in your problems about slope, that needs in your head to translate to derivative. And vice versa. When you read derivative, you need to think slope, right? For our class, that's going to be, I'd say, the main use for a derivative. We will do a little bit of exploration in physics here and there, especially in our final unit, but for the most point, for us, derivatives are slopes of tangent lines, right? And then there are two definitions of derivative that we are responsible for knowing that you see notated here. We're actually going to come back and work with these at a later time, but I like putting them in here now just so we start learning to recognize them. For this class, for the most part, you're just going to be responsible for recognizing that when you see a setup like this one, that this is the derivative of a function. When you see a setup like this one, this is a derivative at the point. Or again, if we were to replace slope, this one here gives you the slope of every point that exists along a function. So you're actually going to get a function answer from something like this, like x squared, right? Versus this, which will give you one particular slope, a slope that exists at, say, x equals 2 on a function. And so this one's going to be a number, -3, a slope of -3, right? That's what a derivative is. So the slopes or derivatives along a function, every possible point, this one will be a function answer versus a number answer, the derivative or slope at one single point, right? Okay. How do we notate derivatives? Well, we have a couple of different ways of notating. You can use either one. You are responsible for recognizing them both. They come from our two fathers of calculus, Newton and Leibniz. So we have prime notation, f prime, f double prime, f triple prime, and obviously this needs to match your function, right? If your function's not called f of x, you're not going to call it f prime, right? If it's called g of x, you're going to call it g prime. If it's called y, you're going to call it y prime, right? So do make sure that this still matches your function. Same thing over here. We have dy dx, this is the second derivative, so it looks like d squared y over dx squared, but it's the second derivative and third derivative of your function here. And again, we would make sure that it matched our function at all times, right? So you can use either one, make sure it matches your function, but you are responsible for recognizing them both. And you will see in some cases people start to kind of borrow some of the attributes of this one over here. So maybe you'll see like an f with a 12 written. Instead of like 12 primes, they'll write a little 12, borrowing the efficiency of this notation into this one. But for the most part, these are our two most typical. Okay? And I do always like making sure that we contrast it. These are the labels of your function. This over here is a direction. This is telling you to take the derivative of f of x. And so when you see this written, this isn't a label, it's a direction. Take the derivative of f of x. Okay? Okay, some vocabulary getting us into the difference between continuity and differentiability. Differentiation, differentiable at x, differentiable on AB. Differentiation is the process of taking a derivative. It means that I can find the slope at points along my given function, right? I'm able to do it. Differentiation is that process of taking the derivative, engaging in taking it, which we're going to be looking at some rules in a short bit here for how to take the derivative. Okay, to be differentiable at x means that the derivative exists at x. So at x equals 2, I have a derivative or a slope of the tangent line. It is 3, right? Something like that. I can take the derivative. And then you have differentiable on an interval, which simply says that for every value that exists on that interval, for every point that lies between a and b, I can take a derivative. I can find a slope of the tangent line at each of those places. Okay? And so what then is the difference between continuity, which we looked at last unit, and this new vocab word here of differentiability, to be able to take a derivative, to be able to draw in a tangent line? Okay, well, I would encourage you to pause the video, go ahead and take a moment and jot down what are the 3 conditions of continuity. Restart the video when you are ready to check them. Okay, 3 conditions of continuity from last unit. F of c must exist. My limit as x approaches c of f of x exists. And f of c equals the limit as x approaches c of f of x. Right? The point exists, the limit exists, and the limit equals the point. Okay, we want to make sure we keep those 3 in mind as we look at differentiability, because there is a connection between the two. They are not the same though, right? There's also a very particular difference between the two. Okay? To be differentiable has 2 conditions. First, you must be continuous. At your point, right, at C. You have to be continuous, or I should say at your x values there, right? If I'm looking at an x value and it's not continuous, well, then I'm not differentiable there, which makes sense, right? If you think about a discontinuity, let me borrow a piece of paper here. If you think about a discontinuity in a function, maybe it's a place where there's a hole, right? Well, this is actually an issue with there's a no point, there's no f of c at this value, there's also no limit. So this breaks continuity twice. But imagine for a second that there's no point at this x equals, we'll call this x equals 2. Okay, so this is discontinuous. It's also therefore not differentiable, because to be differentiable means that I can take a tangent line and draw it in alongside the point. So say we were finding it out here, I can draw in a tangent line at that point and calculate its slope. It would have a positive slope of some sort. But how do you draw a tangent line attached to a point, right? Because remember, this tangent line is attached to this point here. How do you draw a tangent line attached to a point at x equals 2 when there is no point at x equals 2 to attach the tangent line to, right? You can't draw in a tangent line there. There would be no slope of the tangent line, therefore no derivative at x equals 2 if we weren't continuous. Okay, and so that's our first condition of differentiability, is you have to be continuous. Okay, but then there is a second condition, and this is the one that gets people sometimes. No cusps at your x value. A cusp is a sharp turn in the graph. In a similar situation as to why the limit wouldn't exist for potentially that picture I just had up, a cusp doesn't exist because my slope approaching from one side doesn't equal my slope approaching from the other. And so we wouldn't be able to draw in a tangent line here. In picture form, it would look like this, right? If I had a cusp and I asked you to draw in the tangent line at that point where your cusp is located in order to find its slope, right, slope of the tangent line, aka derivative, well, that's a tangent line, right, that I just drew. It has a negative slope. But so's that, and that has a positive slope. And so's that, and that has a 0 slope. right? If I were to ask you to draw in a tangent line, how would you know which one I was looking for, right? There isn't one tangent line. There isn't one distinct answer. And so I don't have differentiability at a cusp, at a sharp turn here. But you want to be careful because this will get people sometimes. A cusp is not a lack of continuity, right? To be discontinuous means either my point doesn't exist, my limit doesn't exist, or my point doesn't equal my limit. That's what it would mean to be not continuous, for one of these to be broken. But right here, I've got a point. I can see it. And I've got a limit. My limit is where they meet up there. And my point equals my limit, right? They all converge right at that location, at that y value. And so I am continuous. I'm just not differentiable at a cusp. Okay? And so we have some examples to explore this before we get into some differentiation rules. Okay, I would encourage you to walk through one with me, then pause the video, try the next one, restart it when you're ready with your answers, etc. Okay? So example 1, on what open intervals is the graph shown to the left differentiable? Okay, so let's go ahead and start with identifying where am I not differentiable? At what x values is my function not differentiable? Well, so I'd be looking for a break in continuity or a cusp. Okay, well the first thing I notice is right here at x equals 3 I have a vertical asymptote, which it would be a place where a limit doesn't exist and also a point doesn't exist. So 2 reasons we have a lack of continuity at x equals 3. And then over here at x equals 6 we have a cusp. And so this would be where my function is not continuous. I'm sorry, this would be where my function is not differentiable. And so then what are my intervals where I am differentiable? It would be from -infinity to 3, 3 to 6, and then 6 the rest of the way to infinity. Okay? If there are questions, write them down now, right? Write them down the minute you have them. Maybe send them to me through email or Remind or whatever. Okay, example 2. I would encourage you to pause the video, try number 2 on your own, restart it when you're ready. Okay, so on what open intervals is the graph shown to the right differentiable? Well, let's first identify where are we not differentiable. I'm not differentiable at x equals -3. I have a break in continuity there. And I'm not differentiable at x equals 2, where I have a cusp. Okay? And so then I'm differentiable from -infinity to -3, -3 to 2, and 2 to infinity. Okay, number 3, go ahead and pause the video, try it on your own, restart it when you're ready. Okay, so same question. Let's go ahead and start with where am I not differentiable? Okay, well I'm not differentiable at x equals -1. I've got a cusp there. And I'm not differentiable at x equals 2, where I have a discontinuity. And so I am differentiable from -infinity to -1, -1 to 2, and 2 to infinity. Okay, so that's your introduction to differentiability, what it means to be differentiable, what it means to have a derivative. A derivative, again, one more time, is the slope of the tangent line. So for example, if I asked you for this function to find the derivative at x equals 4, my tangent line would come in like this, and its slope would be some sort of positive slope. I don't know exactly what. I would have to take the derivative to find that out. Okay? And so that's what we move into now with the end of this set of notes here. As we start to look at derivative rules, you're going to learn quite a few of them over this year. That this one is going to kick us off here. The most common one, the one you will use in probably every single or almost every single derivative you take, is power rule, right? Again, not literally every single derivative, but it's going to be used a lot. And so you want to make sure you get all your questions answered about power rules. So whatever they are, write them down now, ask them the next time you're with me, or email them to me, or whatever you prefer, but make sure you get those questions answered. Okay? So power rule. Power rule is when you have a base that is a variable. Go ahead and call this variable, with an exponent that is a number. And it has to be in this form, in power rule form, so we can't see a root, we can't see a variable in the denominator, right? If you see any of that happening, you have to manipulate the function to get it into power rule form. Okay, but once it's in power rule form, power rule is pretty straightforward. This number that's up in your exponent is going to come down as a coefficient. Your variable base is going to stay the same. And you're going to subtract 1 from your original exponent. So the n that was originally here is going to be n minus 1 in your exponent. Okay, and so I structured these so that we did 3 together, and then so that you would try the next 3 on your own, right? So let's go ahead and work through 3 together. Example 1, find the derivative of y equals x to the 5th. As I look at this, I see a variable as my base, an exponent of a number. It's in power rule form, and so I'm good to go. Okay, so my label, I can either use dy dx or y prime, because this is a y. Right? That label does need to be there. It's part of how you show your function. In this case, my derivative. Okay, then I'm going to take my exponent here, my n, I'm going to bring it down as a coefficient. So the 5 is going to get brought down as a coefficient. I'm going to leave my base, my x, alone. And I'm going to subtract 1 from my exponent. So this is going to be 5 minus 1, which is 4. And that's your answer. Okay, what you have just found there is the derivative, or a function that represents the slope that exists at every point along my function x to the 5th. And so if I had a coordinate point, I'd be able to plug it in to find my slope. Okay? Okay, let's do another one. We're going to do 2 more together here. Example 2. Find the derivative of, okay, this looks real close to power rule form, but it's not quite there. How could I rewrite this root to make it into an exponent like what I need for power rule? How do you rewrite a root as an exponent? Okay, well, a root, remember, is a fractional exponent. And so this would be a 1/3 in the exponent. And so I'd have my x squared with my 1/3. So this would be x to the 2/3. Now that we're in power rule form, we can take our derivative. This is an f of x. So I can't use dy dx, right? This isn't a y. I would somehow need to know that y and f of x were the same within my problem. So that would be like some statement that said y equals f of x. So I'm going to go ahead and use f prime of x for this one. Okay, power rule, I'm going to bring that exponent down as a coefficient. Leave my base alone. My x is going to stay x. And subtract 1 from my exponent. 2/3 minus 1 is negative 1/3. Okay. Okay, one more together here. Example 3, find the slope of the line tangent. Okay, so again, we're real close to being in power rule form. Unfortunately, that denominator is causing us a little bit of an issue. How do I get that x up out of the denominator? Okay, well, to move something out of the denominator means a negative exponent. And so my function is x to the negative 3rd. And now I can go ahead and apply power rule. Okay, so this is f of x, so I'm going to call it f prime of x. Bring down the exponent as a coefficient. So the negative 3 is coming down. Leave your base alone. And subtract 1 from the exponent. Okay, that's your derivative. Now with example 3, I did go ahead and give you a point just so we could take a look at what that meant. So once you have your point here, you can plug it in. So this is an x, y coordinate. So my x is 1. So I'm going to go ahead and plug in 1 for my x. And in this one, I actually don't have a y in my derivative, so I don't actually need the y value there. I just need the x. Okay, which means that my slope at the point 1, 1 is equal to -3 over, right, because a negative exponent brings this down to the denominator. This would be 1 to the 4th, which means that this is -3 divided by 1, or -3. Okay, example 4 is going to be yours. Go ahead and pause the video, restart it when you are ready. Okay, so now we have a g of x in power rule form already, so we're good to go. We're going to call this one g prime of x. All right, make sure your function always matches. This wouldn't be f prime. This isn't an f of x. All right, so g prime equals, bring your exponent down as a coefficient, leave your base alone, and subtract 1 from the exponent. 5/4 minus 1 is 1/4. Okay, and then we have our x, y coordinate point here to plug in. So I'm plugging 16 into my x, which is 5/4 times 1/4 as an exponent, remember, is a 4th root, with x being 16, which is 5/4 times the 4th root of 16 is 2, which is 10/4, or reducing 5/2. Okay, number 5. Go ahead and pause the video, restart it when you are ready. Okay, so find dy dx. So we're going to go dy dx equals, this one's not quite in power rule form. How could we rewrite that? Well, remember, a root is a fractional exponent, so that'd be x equals 5, or x to the 5/2, sorry. So then bringing that exponent down as a coefficient, leaving the base alone, and subtracting 1 from the exponent. 5/2 minus 1 is 3/2. Okay. Example 6. Okay, pause the video, restart it when you're ready. Okay, this is almost in power rule form. Let's bring that x out of the denominator. So it'd be x to the -8. So then we have g prime of x equals, bring the exponent down as a coefficient, leave the base alone, and subtract 1 from the coefficient. Okay. Okay, if there are any questions, write them down now. Get them answered now. Okay. This last page here, we are looking at some nuances on power rule. So making sure we are good with some of the other ways that power rule could potentially show up. The first one is the constant rule. We're doing 2 of them because the answer is always the same. Okay, when you are taking the derivative of a constant, your answer is 0, right? Which makes sense if you think about with example 1 here, which we know our answer is already going to be 0 because we see a constant. Okay, but imagine what we are doing here one more time, just so you can see why the derivative of a constant is always 0. If my function is 5, okay, that is a horizontal line through 5. Okay? If I were to pick a point along this function in order to draw a tangent line in and find the slope of that tangent line, aka the derivative, okay, if I were to draw a tangent line in through that point, my tangent line would also be a flat line. This entire function is flat, right? Well, what is the slope or derivative of a flat line? Okay, well, the slope of a flat line like that is 0. And so therefore, the derivative of a constant is going to be 0. Remember, derivative and slope, somewhat-ish synonymous, right? So in this case, my derivative of y, dy dx, equals, that is a constant, and so its derivative is 0. Okay, go ahead and pause the video, give example 2 a shot, restart it when you are ready. Okay, derivative of pi squared is a constant. Derivative of a constant is 0. And you might be sitting there going, well, that's silly. Why did we do 2 of those if the answer is always 0? Only so that I can make sure to say, watch for pi and e. Watch out for pi and e. Those two are values that look suspiciously like variables, but they aren't, right? Pi and e are numbers in the same way that 5 is a number. Pi is, 3.14159, etc. Okay? E is a number, right? Like their derivatives are going to therefore be 0 still. I can't tell you how many students will get pi squared or e squared or something like that and try to do power rule on it. But pi and e are not variables, right? I don't have a base of a variable, so I wouldn't be doing power rule on it. Okay? So constant is 0. Okay, versus a constant multiple, aka coefficient. The constant multiple rule says that if I have a coefficient out front, it's just going to sit. I'm not going to do anything with it. I'm not going to lose it. I'm going to make sure it stays as part of my problem, but I'm going to focus on taking the derivative of my function. Okay? So for example, in example 1 here, we have find the derivative of h of x. So we're going to go ahead and call this h prime of x. This is almost in power rule form. Let's go ahead and rewrite that x to cube root of x is x to the 1/3, and we're good to go. Okay, the 5 is a coefficient, so it's just going to sit in the problem. I'm not going to do anything with it because it's a coefficient. This exponent, the 1/3, is going to come down in front, get multiplied to the 5. Right, 5 times 1/3 is 5/3. Leave the base alone and subtract 1 from the exponent. 1/3 minus 1 is negative 2/3. Okay, so it's not really different than power rules. We're still doing power rule. It's just, like I said, a nuance on it, making sure we recognize that a coefficient just sits out front. Okay? And so we've got 3 others. I would encourage you to pause the video, try it on your own, restart it when you're ready. So go ahead and pause, try example 2 on your own, restart when you're ready. Okay, find the derivative of y. We have dy dx equals, okay, my exponent here is to the 1st, so 7's just going to hang out. Bringing my exponent down in front, 7 times 1 is 7. Leave my base alone. Subtract 1 from my exponent. 1 minus 1 is 0. Which, remember, something to the 0 is 1, which means my derivative is 7. Which again makes sense if you think about what a derivative is. Derivative is slope, right? Y equals 7x. My m right here is 7. Right? So my derivative is going to be 7. Derivative is slope of the tangent line. Okay, example 3. Pause the video, restart it when you are ready. Okay. Example 3, the coefficient here is 1/3. You could pull the 1/3 out in front if you want, or leave it underneath, whichever one you prefer. Okay, thankfully this is already in power rule form. So bringing my exponent down in front, multiplying it to that 1/3, which is just going to sit in my problem. It's going to be there. Leaving my base alone and subtracting 1 from my exponent. And again, if you want to leave the third underneath the whole thing, so if you wanted to write 4x cubed over 3, that's fine. Right? You don't have to pull the 1/3 out front. Okay, example 4, pause the video, restart it when you're ready. Okay, we have f prime of x equals exponent, bringing it down in front, 2 times 2 is 4. Leave the base alone, subtract 1 from the exponent, 2 minus 1 is 1. So my derivative is 4x. Okay. Okay. Again, if there are questions, write them down, get them answered now. Send them to me through email, whatever you need. Okay? Or remind. Okay, sum and difference rules. So sum and difference rules just say that if you have two functions being added or subtracted from each other, then you can take the derivative of those two functions individually. Right? So same thing, I've got 4 here, so we can practice this. Find the derivative of my y. So again, I can either use dy dx or y prime. Okay, x cubed, we've got power rule. So bring my exponent down in front, leave my base alone, subtract 1 from my exponent. Okay, and then plus, 4 is a coefficient, so it's going to hang out. Bring my 2 down in front, 2 times 4 is 8. Leave the base alone, subtract 1 from the exponent. Okay, this is x to the 1/2, right, because of that root. So bring the exponent down in front, leave the base alone, subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. And at the back we have a constant. And remember, the derivative of a constant is always 0. And so that 3, its derivative is 0. Okay? Okay, example 2. Go ahead and pause the video, give example 2 a shot, restart it when you are ready. Okay, g of x, so we've got g prime of x. Okay, this is exponent of 1. This one is x to the 1/5. Okay, so with my exponent of 1, bringing that exponent down in front, 4 times 1 is 4. Leaving the base alone, subtracting 1 from the exponent. Okay. Bring the exponent down in front, that would be 1/5. Leave the base alone, subtract 1 from the exponent. Would be negative 4/5. And you've got your answer. Okay, go ahead and pause the video, give example 3 a shot, restart it when you are ready. Okay, so we've got f of x here. So we have f prime of x equals, bring the exponent down in front, 3 times 2 is 6. Leave the base alone, subtract 1 from the exponent. And this is x to the negative 2. So bringing that exponent down in front, leaving the base alone, subtracting 1 from the exponent. We've got our derivative. Okay? And then we have a point here to plug in, x, y. So I'm plugging x in, so f prime of negative 1 equals 6 times my negative 1 minus 2 over negative 1 cubed. 6 times negative 1 is negative 6 minus 2 divided by negative 1, right? Negative 1 cubed is negative 1. 2 divided by negative 1 is negative 2. And minus a negative is positive. So negative 6 plus 2 is negative 4. Okay, go ahead and pause the video, give example 4 a shot, restart it when you are ready. Okay, dropping that exponent down in front, 5 times 3 is 15. Leave the base alone, subtract 1 from the exponent. Okay, dropping the 2 down in front, 4 times 2 is 8. Leave the base alone, subtract 1 from the exponent. This one back here is an exponent of 1. Bringing that exponent down in front, 2 times 1 is 2. Leave the base alone, subtract 1 from the exponent. Which means we've got our answer, 15x squared plus 8x minus 2 times 1, which is 2. Okay, the last bit here, your basic trig derivatives. We have 2 that we are memorizing today. You'll see these again in a later video as we look at some of our other trig derivatives, but the 2 basic ones that we are looking at today is that the derivative of sine is cosine and the derivative of cosine is negative sine. Okay? There are reasons why those derivatives are what they are. I'm more than happy to explain that at any point if you would like. Just let me know, but at some point it becomes a memorization thing. You need to make sure you have it memorized. Okay? So here we go. Derivative of sine is cosine, derivative of cosine is negative sine. We're finding the derivative of f of x. So let's walk through one together, and then you could practice one on your own. Bring that exponent down in front. 7 times 3 is 21. Leave the base alone. Subtract 1 from the exponent, which gives me squared. Minus derivative of cosine is negative sine. So negative sine. 3 is a coefficient, so it's just going to hang out. Derivative of sine is cosine. And at the back, derivative of pi. Pi is a constant, and remember, the derivative of a constant is always 0. And so that pi, its derivative will be 0, and plus 0 doesn't mean anything. Okay, go ahead and pause the video, give example 2 a shot, restart it when you are ready. Okay, derivative of y, so dy dx or y prime equals 5 is a coefficient, it's just hanging out. What's the derivative of sine? Okay, derivative of sine is cosine. Then plus derivative of cosine, negative sine, so we have plus our negative sine there. Or you could just put minus sine, obviously. Right? And then back here, this is my minus my 7. And then how do I rewrite that x out of the denominator? This will be x to the negative 1. Okay, so our minus 7 is going to hang out. It's just a coefficient. Bringing that exponent down in front, negative 7 times negative 1 is positive 7. Leave the base alone. Subtract 1 from the exponent. Negative 1 minus 1 is negative 2. Okay, there you go.